Hello everyone, and welcome to a new video series on my channel called Upwork Jobs. So this is going to be a video series where I go on upwork.com, I find a project posted on there, and then I show you how I as an electrical engineer would complete that project. The goal of this video series is to show you how electrical engineers go about solving problems and designing boards for the real world. I also want to showcase some of the problem solving techniques that electrical engineers use, as well as highlight some of the challenges that come with each new project. So today's project is going to be an LED ring light that is designed to work with the Raspberry Pi version 2 camera module. I'm going to be taking you through the entire design process from start to finish. That way you're able to see all the different ways that I mess up before I manage to put something together that looks like it'll work. But before we go any further, please go ahead and drop a like on this video for me. It helps my channel out a ton, and subscribe so you can stay up to date with any future videos. And with that out of the way, let's just jump right into it. So the first thing I want to show you, of course, is just the job posting, kind of what we have to work with and the project specifications that the client has listed on here. So the title of this is Raspberry Pi Project Circuit Design, LED Driver PCB Board Specification. So this project is for an illumination ring for a Raspberry Pi V2 camera board. Take close-up picture less than 2 inches from camera lens. Here the list of deliverables for the project being either 5 working boards or a board layout and parts list ready to order. They also mentioned that the external power for this board is going to come from the Pi Sugar 2 universal power supply, and that this LED board needs to interface with that Pi Sugar 2 power supply. The driver IC needs to power 6 at minimum 100 milliamp LEDs, needs to be adjustable 0% to 100% by commands from the Raspberry Pi Zero, and the LEDs need to be stable at a set percent. Cannot flicker. So here's kind of what we have to work with. So the first portion of this design that I want to kind of take you through is what I refer to as the preliminary design notes. This is where I kind of vomit onto the page everything that's kind of going around in my mind as I'm reading these project specifications, right? So you're going to see a lot of things that I write down that don't end up panning out. There's a lot of different avenues that I quickly jot down, here's what we could do, here's some other potential solutions, things like that. So the first step for me when it came to completing this project was I needed to familiarize myself with the components. And by components, I mean the Raspberry Pi Zero, the camera board, and the Pi Sugar 2 universal power supply. So I've worked with plenty of Raspberry Pi Zeros and boards exactly like them before, so I'm already pretty familiar with how this thing works. However, I'd never actually worked with a Raspberry Pi camera board before, nor had I worked with the Pi Sugar universal power supply. So I need to do a lot of research onto how these things worked and how they work together more specifically. So real quickly, I just want to take you through show you kind of what it is exactly we're talking about here. So this is a picture of the Raspberry Pi camera module 2. So this is the Raspberry Pi camera module 2. So I'll just take you through some quick snapshots, and there's how it connects with our Raspberry Pi. Now this is a Raspberry Pi. This is not a Raspberry Pi Zero. And then the Pi Sugar 2, this is the Pi Sugar 2. As you can see, it's just a battery packed with a battery management IC. It has these little button hook connector things. And it looked like, based on that picture, that's how it interfaces with the Raspberry Pi Zero, is it connects to these little holes, these little through holes right here. It snaps into them, and then that's how it connects things like 5 volts and ground and any signals that maybe need to be sent to the battery pack back and forth. So the next step for me was to take a closer look at the camera board and start to flesh out some early design ideas. The first bullet point I have here is maybe we could take advantage of the already existing mounting holes. So if you see right here, we already have 4 mounting holes on the Raspberry Pi. I thought it would be very nifty if we could already take advantage of those, and we can design our board to work with those mounting holes, meaning our board just has mounting holes that align perfectly with those. So any sort of mounting techniques that are already in place for this camera module, they might be easily adaptable to work with our board itself. The next bullet point is maybe our PCB could go around the camera in a horseshoe shape. So this is one of the early ideas I had, was that I knew we need some lights around this camera, and then I knew we couldn't obstruct the actual camera lens itself, or else the camera wouldn't work. So that kind of gave me the idea, is I already saw a horseshoe pattern forming around our camera module, right? Like this maybe. And then we could put the LEDs just around the perimeter right here, and then it would act as, a nice light source that wouldn't obstruct the camera lens. The next bullet point I have is maybe we can use a similar connector to the one on the camera board. So if you look at the camera board, they have sort of a like ZIF connector, has a very low profile, it's surface mount. It doesn't take up a lot of space on the PCB, which are all really attractive properties because we have a lot of the same problems that we're dealing with on our own board. So I did some research to figure out what connector they use, and I looked around the connector type, and I kind of saw and looked up like what connectors can we use that fit our purpose exactly. Because I have another note here is I jotted down, here's the signals in my mind that I think we'll need to control this. Of course, we'll need power. Of course, we'll need ground. And then I think we just need a control signal, right? Some type of like maybe PWM signal or an analog signal to be sent to control our LEDs, turn them on and off. All right, so while this camera board has something like, I don't know how many positions that is, like maybe 16, 24, ours will only need 3. So we could find a much smaller, simpler connector maybe than the one they use, but it's still good for inspiration. Another point I have here is that ours should be right angle as well, because it also provides like a lower profile and it works much better from a mechanical standpoint. Just to have, we can sort of closely route our cables together. So if there's any sort of like housing or something that the camera board is already made to go in, ours could again easily adapt to that. I should also mention that I have this bullet point down here that says could go connectorless, solder wires directly to the board, maybe. After all, we can just use some little like mounting hole type vias right here. You could just stick some wires through and solder them on, and that would work just well because we only have 3 wires, remember, so we don't really have a huge problem where we have to solder like 10 or 15 wires or something like that to the board. So that is also another possibility that I had. Then after I kind of fleshed out some of the preliminary ideas, what I wanted to do was go take a look at some of the connector options that I had for my board. I just went to molex.com. This is one of the connectors I found. This is one of the early ones that I found. It was just a small 3-position surface mount, low profile connector that I thought, you know, maybe this one will work. So I just quickly said, okay, this is a good starting point. Let's see how this works. So I just quickly copied the part number, copied a link to it, and I just posted here, and then I just kept going on, right? So this is very much like idea, throw it at the wall, see what sticks, okay? So the next thing I wanted to take a look at was how I was going to power the LEDs. I already knew that there was a 5-volt power supply on the Pi Zero, but I wasn't exactly sure if like all the 5-volt nects were connected, or if there was enough current capabilities from the 5-volt power supply, or like what it was, right? So I needed to take a closer look at that schematic, and then also how it worked with the Pi Sugar 2. So what I ended up discovering was that all the 5-volt nets on the Pi Zero are interconnected. They all come from the same 5-volt power supply, and then that 5-volt power supply in this case actually comes from the Pi Sugar 2. So then I had to go and see what was the Pi Sugar 2's current sourcing capacity, and I found out that it was up to 2.4 amps of output current. And if you do the quick math of 6 times 100 milliamps, that's 600 milliamps of total current draw, like maximum at one time. And so I wanted to know, could the Pi Sugar 2 handle this? And so the answer is yes. However, there's a huge asterisk I want to put there, is that capacity of the battery is really not that big. And so 600 milliamps of current would drain it extremely, extremely fast. So I put a note in here is probably going to recommend 25 milliamp LEDs. And I think this highlights a good aspect of like preliminary design phases, which is you do kind of a feasibility, like back of the napkin type of thing. Like, is this even feasible? And so that's why I put this note here. 25 milliamp LEDs would reduce our 600 milliamp load all the way down to 150, which would make the battery last a lot longer. So I think it's like worth bringing up to the client, like, hey, this might actually work a little bit better for what you want. So let's maybe start with the 25 milliamp LEDs, and then we'll see if they're bright enough for you. And then if you still don't like them, we can always go up, right? But the last thing we want to do is we don't want to be just draining your battery nonstop. So then moving on, I just went into the circuit draft. And also I kind of want to mention is I'm not necessarily trying to come to some complete ultimate conclusion for each of the portions of this little like sections right here. I'm just kind of like jotting down some of my initial questions and I'm moving on, right? Jotting down and moving on. I just want to kind of keep it moving and try to flesh out many different, I don't want to go, the mistake that I think some people might make, or the mistake I don't want to make, is that I get like really, really detailed in one portion of the project without having explored any other portions of the project. And then I get to them and I realize, oh, there's something I didn't even think about that totally nullifies this extremely elaborate, detailed design that I've already spent hours fleshing out when it's not even feasible because I have something I missed, right? So like we're doing like a surface level passover for each of these portions of the project, kind of writing down some of my initial questions and thoughts, and then just keeping it moving, right? At least that's how I kind of go about designs. So for the circuit draft, right off the bat, I thought, okay, we're going to use some transistors to drive these LEDs, and then we're going to use a signal from a GPIO pin on the Pi 0 to control the LEDs, to use the transistor basically like a switch. And then we can use the 5-volt supply as the actual power source. Okay, so I quickly put here GPIO pin is a 3.3 volt. And then I said, I think we want to supply around 1 milliamp, because in my mind, I also already knew that typically GPIO pins can source like maybe 16 to 20 milliamps of current. And I knew he said 6 LEDs, so we're going to have about 6 of these. So I knew that if we had about 1 milliamp per base pin of the transistor, 1 milliamp per transistor, that means we'd have about 6 milliamps of total current draw. So I thought that would give us some good margin for not like wearing out our GPIO pins. And then like if we even went up to like 2 milliamps, that's already 12 milliamps, which is pretty close to the limit. So that's kind of where I got my like back of the napkin 1 milliamp first initial thoughts on, right? And then I thought, okay, we'll put this LED here and I have 25 milliamps right there. And then I also did like a feasibility, like back of the napkin calculation. I said with a base of around a DC current gain of around 100, 1 milliamp should be more than enough to conduct 25 milliamps of current, right? So I thought, okay, this is extremely feasible. We can easily do this. So then the next part that I wanted to work on was like an initial BOM draft of kind of like do an inventory of all the different components I think I would need for this board. So I know I need a connector. Well, I think I need a connector. I definitely need an NPN transistor. And then I also listed some of the preliminary characteristics of this transistor. And at this point in the project, I remember actually like went on DigiKey, and then I found a transistor that I thought might be a potential candidate. And then it also gave me some like an initial introduction to some of the characteristics of the transistor that I also listed here. For example, I'm talking about things like the collector current rating. So it's just how much current can flow through the collector. So I knew I wanted something probably greater than 50 milliamps. There's also something called the collector to emitter voltage rating. What's the total voltage drop that is allowed across the collector and emitter? And then something greater than 10 volts is kind of what I picked for that. And then I said I wanted as small of a package as possible. All right, so these are some of the initial component characteristics that I selected, and then I found a transistor that kind of fit these characteristics, and that's kind of what I used to go off for the rest of the design. And so my mind was, I thought, okay, if this doesn't work, I'll probably be able to find something relatively close, so my design probably won't change too much, even if this specific component does not work out for me. Then I did the same thing for the LEDs. I just started kind of browsing LEDs on DigiKey, kind of searching for what I wanted. Like I'm like, okay, I want something like 25 milliamp current rating, maybe a little bit higher. Kind of looked at various package sizes and started getting some ideas like how big are these things going to be. And then I found a potential candidate for the LEDs that we're going to use. I just threw that down on here as a starting point, right? Then I could get things, important characteristics for the design, such as like the forward voltage, like the current rating, the package size, things like that went into my later on calculations. So again, like just threw something on the paper as a starting point. I knew my design probably, like, even if this specific component didn't work out, that it would be close enough to get me where I needed to go. Also knew that I needed some current limiting resistors, and then I put the package size down because I figured 0603, and if that's too big, we'll go with like 0402 because I know that forward area is at a premium here, so we might really have to find something small. 1% tolerance because I definitely know that we want to finally control current through these LEDs and the transistors. And then I said like 0.1 watt rating to start with, seems fine. And then one really interesting part that I have here is like an initial PCB draft of like what my PCB will physically look like. So here I have like the little horseshoe pattern drawn. I went and found a mechanical drawing, and we'll explore that even in greater detail. I found a mechanical drawing. This is a mechanical drawing of the Raspberry Pi camera module V2. So I used that, and I kind of drew out some very preliminary dimensions. So I knew that it was like 25 millimeters by 23.862 millimeters. So I'm just kind of starting out as our camera board as a reference. And then I'm kind of working around that. Basically, I said, okay, I know we definitely want to make this is our little like cutout for this is where the camera is going to go. Put a note for, okay, the mounting holes are 2.2 millimeters in diameter. So that's what these are. We're going to use the same ones to have mounting holes that are that can interface very well with our camera board. We want a rectangle cutout right here. Like I said, I put a note 4 layers. I was thinking, okay, this board's gonna be extremely dense, and so we might need to, if you can't scale horizontally, then the next thing is to scale vertically. So 4 layers might be a good option for us. That way we can get all of our traces routed. Then I also put a note here is transistors and resistors on bottom layer. This is, again, I thought, okay, there might not be enough space for everything on the top layer, so putting stuff on the underside could give us more room depending on how big these LEDs turn out to be. With my initial PCB draft completed, that concludes the preliminary design notes phase of this project. Now I think I'm ready to take a closer look at the circuit and start fleshing out some very real like numbers and stuff. So this is the diagram that I drew in the preliminary design notes phase of the project. And after looking online and seeing how other people have gone about designing circuits like this one, I kind of realized that this probably is not going to work the way I want it to. Mostly because the LEDs that I was using for this project typically have forward voltages that are like 2.7 volts and above. And with a 3.3 voltage on the GPIO pin, I did not think I was going to be able to overcome both the voltage drop from base to emitter as well as the forward voltage necessary to get any current to flow through the LED. So I kind of thought this is kind of not how I want to go about doing this. And I quickly drew a calculation of KVL of the input loop. So we have like 3.3 volts minus the base emitter voltage drop equals 2.6 volts. So I couldn't find any LEDs with forward voltages that were lower than like 2.71 that were the type of LEDs that I needed to use for this project. So I had to kind of rethink how I wanted to do this. So after looking around a little bit more on the internet, I realized that there's configurations kind of like this that use a transistor in what is known as saturation mode. And that means they basically use the transistor as a sort of switch. And we'll go into that in more detail in a second. But in this mode, we're using the 5 volt source to overcome the forward voltage. And then we're also removing the diode from the emitter loop. So the input loop, when you do KVL, there's no longer this massive forward voltage required on the input loop. So you can actually get some current to flow through the base pin and down through the emitter pin. So just some quick notes. So first, let's talk about the input loop because that's still relatively the same. And then we'll talk about how saturation mode changes things on the output loop. So on the input loop, we want to make the base current equal to 1 milliamp to ensure that much greater than 25 milliamps can flow through the LED. Because if you remember, transistors are basically like current amplifiers, and we know that the collector current is simply a product of the base current and our DC current gain, which is like, in this case, I found it to be around 200 for the transistors that we spec'd back in the preliminary design notes. So I'm using that one for our calculations now. So we're going to use a current limiting resistor to limit the current through the LED, which is going to be R2 in this case. We connected the anode side of the LED to the collector pin, so now the 3.3 volts will be able to generate our base current necessary, our 1 milliamp. And then I have a calculation that shows Kirchhoff's voltage law on the input loop. So we have 3.3 volts minus the base emitter voltage drop, which is a standard 0.7 volts, minus the 1 milliamp times our R1. It's equal to 0. When you do the math, you get R1 equals 2.6 kilo ohms. And that's what this R1 value needs to get in order to achieve around a 1 milliamp current through the base pin. So now we're going to do KVL. We're going to do the calculations for the output loop. And this is when the transistor is in saturation mode. Just a really quick summary or brief description of what saturation mode is. Saturation mode is when the collector current is not equal to beta times our base current, like in this configuration. So that means if we had 1 milliamp in the base, we're not getting 200 milliamps of current through our collector pin. And this is because we have a current limiting resistor up here. That's what it means for the transistor to be in saturation mode. Just a quick calculation at 1 milliamp, we have the collector should equal to 200 milliamps and we're limiting IC to 25 milliamps. Then for Kirchhoff's volt for the output loop in saturation mode, it looks something like this. So we have our 5 volts minus 25 milliamps times R2 minus the forward voltage of our LED, minus, and I'll call this like I forgot the term that they use in the data sheet, but it's just like the collector emitter voltage drop. And this only occurs in saturation mode, or this is a value that's specified on the data sheet for whenever the transistor is in saturation mode. Doing the math, we get R2 is equal to 80 ohms. So now we have solved basically the equations for our two resistor values, and we can actually start designing the circuit. But before we start actually putting things down in our schematic, I wanted to really quickly just do a quick circuit simulation just to make sure that I'm not crazy or missing anything. So I know this maybe looks really complicated, but here we have what's supposed to be our GPIO pin, 3.3 volts. Here we have our 5-volt voltage source, and then we have our 1, 2, 3, 4, 5, 6 LEDs. I put 100 ohms for our current limiting resistor because that was like a close nominal value for our resistor. So I just went with 100. And then I went with 2.5K for our current limiting resistors. Okay, so that means up here we have a total current draw from our GPIO pin of 6.286 milliamps, which is good. That's well within our 16 milliamp capacity. And then we have a total current draw from our like pi sugar in this case of 153 milliamps. And then through each LED we have, this is the emitter pin, so it should be a little bit less actually, because if you know that the emitter is equal to the base plus the collector. So this is about right actually. So 26 minus like 1.048, roughly 25 milliamps to each of these LEDs in this configuration. So this was just, like I said, a sanity test. It's always good to simulate your circuits before you start designing them because you never know, like you could miss something crazy here. So with our circuit properly simulated and our components all calculated, we can actually move on to doing the schematic capture of our board. So the main components for the BOM are kind of listed here. We have our connector, we have the mounting holes right here, the 2.2 millimeter ones. Then we have, like I said, our current limiting resistor, and then we have another current limiting resistor that's connected to the LED PWM net. So this is kind of how it's set up. So just 6 copies of the same circuit. Again, this is a pretty like simple circuit. So I guess we'll just kind of start with the connector. So we have our 5-volt power line, we have a ground line, and then we also have the LED PWM line, which is going to connect directly to the GPIO of the Raspberry Pi Zero. Like I mentioned, we have our 4 mounting holes, which are 2.2 millimeters in diameter. And then let's just take a look at one of our like LED driver circuits. So like I mentioned, GPIO pin 2.61K is what I found on DigiKey going into the base pin of our transistor, which goes, then we have our emitter connected to ground, and then we have our LED connected to the collector pin, and then we have our current limiting resistor here, and then we have our 5-volt net connected right here. So again, the circuit is actually extraordinarily simple. There's honestly not much more I have to say here. Like after we lay it out like this, we can go straight to layout. Okay, so now we're ready to talk about the PCB design phase of this project. So here I have a quick process overview kind of written out. And the main point I kind of want to illustrate with this process overview is we're starting at a very mechanical level and then we're getting to the electrical level. So we're not starting out by placing components and routing them. We're starting by like getting our board shape, placing our mounting holes and our connectors. And the reason for this is that these mechanical constraints are the least flexible portions of our project. And so they need to be defined first because they can't be moved. Like if we started like routing and placing components first, and then we realized, oh, this mounting hole doesn't work with our current routing configuration, we can't just get rid of the mounting hole. Like it's there, like you got to deal with it, like your in-laws. Okay, so just the quick notes I have on setting the board shape. So started out with a mechanical drawing of the camera board. So I've talked about this before. So I used this heavily when it came to designing my board. So I started out by making a nice like 25 millimeter by 23.862 millimeter board, square board, just like this. And then I added in my little cutout, which came out to be 8.5 millimeters. So the way I got that value was, I think I used this 12.5 millimeter center camera thing. And I knew this was 8.5 millimeters right here. And so I just knew I needed to cut out around the camera that's at least 8.5 millimeters. And the way I got this 8.5 millimeter value was that on this drawing, it says right here that the camera is about 8.5 millimeters wide. So I knew this was like a minimum starting width. Like I said, in that preliminary design note, I said if I can get it out a little bit further or farther, that would be beneficial because I wasn't 100% sure what the viewing angle of this camera was like, and I didn't want any obstruction to occur because this is going to sit a little bit on top of the board. And so there could be a little bit of obstruction if the viewing angle is wide enough. So that's where I got the 8.5 millimeter value from. Then I also wanted to add in some rounded edges. So if you see here, these 2 edges or these 4 edges are all rounded, and this is just to conform to the original camera module. And because the reason I wanted to conform was that is like I mentioned earlier, there could be some like third-party cases that this camera module is made to go inside. And so for us having rounded edges, it could help it more, like our LED board, more easily integrate with whatever, third-party cases that are being sold. So that's why I did that. And yeah, so here's I just want to give you a minute to look at, here's the bare PCB with all the dimensions. Alrighty, and so the next step was for me to place what I would refer to as the critical features. So these are going to be things like the mounting holes and the connector. I have a note here. Aligning the board's mounting holes with the camera board is a high priority. Our board needs to be able to securely mount onto the camera board. The assembly also needs to be able to mount. So by assembly, I mean the camera board plus our LED board needs to be able to mount. So this is going back to that what I mentioned. There could be third-party cases. Say our client has already designed their own case. We want to make ours as easily to work with as possible. I have another note is we want to make sure to orient the connector in the same direction, and having it in the same place as the camera board is a high priority. So putting it on the top right here, just like that one. So putting it up here, just like it is on the camera module, so that they both kind of point the same direction, goes along the same line of thinking as we want this to mechanically integrate with whatever our client's using it for as easily as possible. So some key takeaways here. Critical features are often physical mechanical constraints imposed onto us by other parts of the product. It is important to start with these because they are the least flexible. Kind of that rant I just talked about earlier. So the next part that's pretty exciting is we get to kind of plan the layer stack up. This process was actually a lot more trial and error so the next step for this PCB layout is to plan the layer stack up. This process was actually a lot of trial and error. You look down here, I actually mentioned there are two major solutions that I tried out, and I ultimately went with one of them, of course. I knew we would probably need a 4-layer board because of the component density. So that's like right off the bat, I started with like a 4-layer idea, and I had some ideas how we wanted to do this. So my plan was to have the power, ground, and signal layers run under the components and just have very short traces with vias connecting the different nets. So I have a little diagram right here. So imagine the top layer, got all your little components here. Then you have a via to the LED PWM line, a via to the power line, and you have a via to the ground line. And then if there's any interconnections that need to be made, they can just all be made on the top layer where the components are. And real quick, I just want to go back to our schematic. Like I wasn't 100% sure what this little thing would look like at the end of the day. Like I knew we had a resistor going in here, and then I imagined this is going to be a via right here. This was going to be a via right here. And then this was going to be a via right here. And then we would just have trace from here to here, and then trace from here to here, and then trace from here to here, basically. So I figured we could put these all really close to each other, and there wasn't going to be like a lot of wild routing. So I thought we could get away with like my via solution was my first idea. And then I have listed what I'll refer to as 2 different component arrangements, which is just like how I planned on arranging the components on the board as a whole. And I'll describe what these are very specifically. So we either had all components on the top layer, which I just mentioned, or we could put all the components, or we can put components on both the top and the bottom layer, right? So if you can imagine this diagram that I just drew, components up here, via down, 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 or we would have a component here and then send a via wherever it needed to go, right? So via like here, or even to the top layer, right? And so they would just go back and forth. So the benefits to all the components on the top layer, or sorry, the pros and cons, I guess I should say, as I listed there is, so con, I thought this was a con, is that it's going to be super, super tight up there. There's hardly any real estate. Like I don't even know if I'll be able to fit all the components on the top layer. A pro that I listed though is we'd have a really good solid ground plane. So my worry was that on the ground plane, if we had a bunch of components there, it would kind of break it up and it would be a little bit fragmented, and we wouldn't have a really nice, wide, even ground plane across the whole bottom of the board. So I wasn't sure if I'd be able to get away with that if I put components on the bottom, because there would need to be other connections that went to like our power, our PWM, or even our top layers. So there'd be a lot of vias as well as actual component bodies taking up some copper space. I put a note here that says more robust question mark because I wasn't actually sure, and we're not actually sure how our client plans on mounting this board like to their LED board, like to their camera board. We wanted to give them we wanted to make it as easy as possible and give them lots of options. However, they could do something that ends up being like, if there's components on the bottom side or the top side, it could end up being like these components could end up facing a lot of physical strain and stress, right? I put more robust question mark just because we could either put them all on the bottom and they'd be protected, or put them all on the top and they would be protected. And then another highlight here, another pro, is it's going to be cheaper to manufacture. If you put all your components on one side of the board, that's just one less run that the manufacturing process has to go through in order to like flip the board over and run it on the underside. Okay, so we would save in manufacturing cost. So then the pros and cons list I made for components on top and bottom layers, it kind of follows the same suit. Here we have more room for placement. So we might actually be able to fit all the components, and we'd have a little bit more room to play with where the LEDs needed to go, where our connectors need to go, kind of like everything like that. If we have more real estate with a top and bottom arrangement. I put weaker ground plane question mark. I wasn't 100% sure how our ground plane would come out if we did a top and bottom. Like I mentioned earlier, I was worried it would be a little bit too fragmented and we wouldn't have good conductivity all the way around the horseshoe. If we had the ground plane was a little broken up, like say the traces in some areas just got really thin, I was just worried it wouldn't be a good ground plane. I put a question mark there. I was unsure about that. Components could be damaged more easily. Like I just kind of mentioned talking about, if you have them on the top or just the bottom, you can kind of protect them a little bit easier depending on how they're going to be mounted to the rest of the assembly. And then of course we know that a top and bottom arrangement is going to be more expensive to manufacture, as I just mentioned, because then they have to go through 2 runs of the PCB manufacturing process. So ultimately after I experimented with both of these. That's what I want to say is like, I tried putting them on the top and bottom and kind of seeing how the routing would go. I also it felt like I needed extra vias. That's one thing I probably should have mentioned on the top and bottom layers. I needed some extra vias because let's say this transistor is on the bottom layer and this resistor is on, or an LEDs on the top layer. I need a via between these two. So that's like an extra via that I would need. And so again, that's like another like fragmented or breaking up of like our ground plane. And so I just didn't like that much. So I ultimately went with the top layer. After I kind of fiddle around with all of the components and realize, okay, I think I can actually fit them on the board. And so that's kind of what I ended up going with. And so that's a great segue into placing the components, right? So here's how I have here's the mechanical placement of all the components, right? So here's kind of how I went about placing the components. You can see actually there wasn't even enough room for me to put the designators on all of these. So that's how tight it was. So I just let them off and I figured it's a simple enough circuit where I didn't need them. So I just kind of rolled with it. So these big ones right here, these are the LEDs. Right here. So these 3 right here, then there's this one and this one, and then this one. And so let's just check my notes real quick so I can see what I wrote. So again, we did a lot more trial and error with this to kind of get it right. It started by placing one complete circuit. So I went with something like this. So I found like I gathered all the components for this one complete like circuit right here. And I saw like, here are all the different ways I can arrange them being placed. And then here's the configuration that this arrangement results in and stuff like that. And here's where the vias kind of go. Here kind of what it looks like, right? So again, it's just trial and error. And I saw like which one I end up liking most, which one gave me the most room for like lots of vias, which one gave me, I wanted things like really, and we'll talk about this in the routing portion, but I want to be able to have, or not very wide traces between everything because it's more of a power circuit. So there's going to be a lot of heat dissipation. And then we also want really good grounding just for, again, like heat dissipation and efficiency and stuff. I started by placing one complete circuit. Yeah, see differentiations. Although it looks symmetrical, this is a good point. Although it might look symmetrical, each circuit has some differences. So this board, actually, you would think it's a symmetrical board, like from a board perspective, right? However, these components themselves are not symmetrical. Like I can't take this transistor and like flip it and reflect it across the y-axis, right? So this component is going to have to be here like this over here. It's going to be the same orientation over here. However, like where all the pads and pins are not going to be in the same spot relative to this other component, if that makes sense. So this was like a 1-by-1 like trial and error, seeing how I could fit each and every single component on the board, right? So kind of here's what it kind of came out to look like. Okay, so then when it came to routing everything together, like I mentioned, we want super wide traces. We use as much as possible because it's like power circuit, and we know even actually these LEDs have an additional third pad under here that I connected to ground for heat dissipation, because these things are like a lot of current is going to flow through these. So, and again, we kind of followed my idea of we want a short trace and then drop a via. So I'll kind of just give a good demo right here. So here we're just taking a look at, we have like R1 right here. So we have the 5-volt net, and then we're dropping a via, connecting it to the 5-volt net, which I just made this green layer right here. And then we have LED PWM is this layer right here, and then the bottom layer is our ground. So that's kind of like the theme with all these, is we just very short trace, drop a net, very short trace, drop nets, like ground, short wide traces, short trace, drop a net. Sorry, I keep saying drop a net, drop a via, short trace, drop a via, very short trace, drop to LED PWM. That's kind of like how I went around the whole board, right? Very short wide traces all around. That's kind of how I went about routing the whole thing. And so the last thing I kind of want to talk about is potential improvements. Like as engineers, we often have, even actual companies do this, is they ask you to reflect on your design and make some improvements to it, and then they will like do a a new revision. You know, it's like the camera module version 2. That means there was a version 1. And so what did they do? They looked at version 1, said, how can we improve it? And then they made a version 2. So if I can make a version 2 of this board, what would I do? And first bullet point I have here is, well, a 2-layer board might be possible. It's possible that we could use some sort of split plane on the bottom layer that has like all 3 of them or a couple of the signals on the bottom layer as sort of a split plane configuration. We just use some like copper pores on the bottom layer, if that makes any sense. Basically like break up the horseshoe bottom into like, you know, 2 or 3 different sections and then just route to those that way. And so we could cut down from a 4-layer to a 2-layer. I don't know how much of an advantage that would give us really versus like we would be saving on cost. But I don't know how much that would reduce the efficacy of our board. So that's kind of something I would want to explore for version 2. And I said it might be possible just to get away with wide traces instead of entire planes, because I used entire planes for our signal, power, and ground layers. And like the whole aim of this is to just reduce the cost of manufacturing for this board. But then another bullet point I have here is a circuit that only requires 1 resistor might also be possible. So this is a configuration I came across whenever I was searching on the internet for how other people design boards kind of like this. I saw a configuration that had a transistor with only 1 resistor on the emitter side, just like this. However, I knew for a fact that my saturation configuration was going to work. And so I just kind of went with that as something that I knew would work, again, because we're on like a time crunch and stuff. So that's something I would explore a little bit further if I had more time, basically. And with that pretty much wraps up everything I wanted to talk about in this video. Thank you so much if you made it to the end of this video, and hopefully I will see you in the next one.